Let's go ahead and just start off with your background. Maybe just tell us a little bit about yourself.
I grew up in Connecticut, went to public high school, kind of standard background, played a lot of video games, hung around on computers quite a lot, got into programming like kind of early, was like taking, like APCS classes in high school, like, playing around with Linux, things like that. Then I went to undergrad at Northwestern. At Northwestern, I was in this honors program called the Integrated Science Program. It's kind of like this unique program that mixes math, physics, CS, biology, chemistry, et cetera. And I got kind of like widely exposed to a bunch of different sciences, which got me just like very interested in kind of like diverse applications of math and CS like across the board. So I ended up triple majoring in ISP, math, and physics. And then I wasn't actually a CS major, but I took a bunch of CS classes. Like I took algorithms, artificial intelligence, data structures, et cetera. And then I was always kind of just like hacking on the side. Like I did like theoretical chemistry research for all 4 years, was always like programming for that. And then I also was like constantly playing around with like Arch Linux and like Manjaro Linux and like things like that. Always kind of just like building little tools and like playing with operating systems and stuff. So yeah, then at PhD time, like when it was kind of like I knew I wanted to go to grad school because I was very interested in academics. I thought research was really cool. I thought there were a bunch of really interesting topics at the time. I had to sort of decide like what area I wanted to go into. I was originally leaning towards physics actually, and was going to do maybe a PhD in like condensed matter physics, applied to a bunch of programs, got in, was seriously considering them. But I was always sort of like attracted to the generality of CS and math. And I felt like if I did a PhD in applied math, I might be able to kind of like keep my feet in all three squares at the same time. Like I could play with math, I could play with CS, I could play with physics, I could solve the problems that I wanted to, and I maybe didn't have to fit into any one box. Like I felt like as an applied mathematician, you can kind of do anything, and I felt maybe like a little bit more limiting if I went like straight into condensed matter physics. It's not clear that that's actually true, but that was kind of my logic at the time. Did a PhD at Harvard. I started in kind of physics related things. I mean, at the time that I was there, the applied math program at Harvard was very much oriented around like soft matter physics and mathematical modeling. And I liked it quite a lot, but I always loved algorithms and CS. One of my favorite classes in undergrad was AI and ML. And I sort of felt like I was missing that. And then at the same time, like ML was sort of exploding, like AlexNet happened in like 2014. I started my PhD in 2015. Like, like things were clearly cooking. And so I was at Harvard, MIT was down the street. I decided to go over to MIT and get more involved in the ML community there. And I picked up a co-advisor, Jean-Jacques Slotine, and he kind of got me like really deep into deep learning, control theory, reinforcement learning, et cetera. And then that kind of like kicked off this like really interesting journey sort of at the intersection of ML and applied math. I interned at Google, which I spent a year there, and I got to kind of work on a bunch of really cool ML and robotics problems. And then, yeah, from there, I've kind of always sort of like occupied my little niche sort of at the interface of applied math, CS, and ML. And I think it's a great space, and I love it.
Awesome. So maybe tell us a little bit about your experience. Before getting to CMU, you were at Current, the Current Institute of Mathematical Sciences. Tell us a little bit
Yeah.
about that, and then when you got to CMU, at the beginning you were sort of an assistant professor in the Department of Mathematical Sciences. Now you're at MLD in the ML department. Tell us a little bit sort of about your journey being a professor.
Yeah, I mean, these are all kind of like, these are great observations. They're all kind of like variants in the same theme, even like going back to what I just described, starting PhD. So, when I was trying to decide where to do my postdoc, I kind of had to make a decision. Do I want to go like all in on ML, or do I want to like continue to toe the line? And I had some postdoc options at like Berkeley, for example, that were like very, very good, like core ML uh, options. But I wasn't sure that like it was going to like take advantage of my background in kind of a maximal sense. Like I felt like I'd be throwing out like a lot of the work that I did in physics and applied math, and I wanted to find an angle that was sort of like again sort of threading the needle. And so then I came across Eric van den Enden at Courant, who is a genius. I felt really fortunate to work with him, and he was kind of like getting very interested in precisely this. For a while he was doing problems in theoretical chemistry, scientific computing, et cetera, but always kind of centered around like stochastic analysis and sampling. And this just fits in basically perfectly with the math that underlies generative modeling at the moment. So I went to Quran to work with him, and he got me really into generative models. that has kind of just been like a bit of a match made in heaven.
Mm-hmm.
I just really love the area. I think like the math is beautiful. What the algorithms can do is amazing.
Mm-hmm.
It's a really cool space.
Mm-hmm.
Um, so I came to CMU for many reasons. I mean, I really liked the place and I love the math department here. But like one of the strong draws was like always just like the strength of ML. So I
Mm-hmm.
started as kind of like a courtesy appointment in MLD,
Mm-hmm.
but then I was kind of constantly interfacing with them. I mean, I had like 6 collaborations with people over there last year,
Mm-hmm.
sort of mostly working with students from CS and ML.
Mm-hmm.
And so then eventually it sort of just made sense to formally join the department. And so now I have a 50-50 appointment, which is really great because it means that I kind of get to continue doing what I've always been doing, which is I have kind of like one foot in the math community and one foot in the ML community. And I think that this is, a very nice niche that like
Yeah,
not so many people at CMU had filled. And so I'm like
indeed.
I feel really fortunate that I kind of was in the right place at the right time to get this position.
Yeah. So maybe tell us a little bit more about this niche. I mean, it definitely is unique at CMU. I mean, there are a lot of people working on LLMs across a lot of departments, including LTI and RI and a lot of these other departments. And I mean, even with an MLD, which I would say, skews a little bit more on the theory side compared to some of the other six departments in School of Computer Science, not everybody's working on the mathematical side. So maybe just tell us a little bit about that experience. Like, what do you feel like you learned, doing that? What are some trends and patterns you've seen and like what makes successful people in that intersection?
Yeah, so I mean, it's an interesting space because the history of ML has been that like it actually originally was a rather mathematical subject, mostly
Mm-hmm.
kind of like leaning on statistics, right?
Right.
But then more recently, like deep networks have kind of thrown a lot of this out of the window,
Indeed.
and it kind of, I mean, I love theory, but there's some element of like the more recent results
Yes.
empirically on very large models drawing into question a little bit the validity of some of the theory. Um, the approach that I take is like a little different from this traditional mathematical or theoretical view in that like it's really using applied math, whereas like the history of ML has sort of been grounded in statistics. And I
Mm-hmm.
think the typical tools of applied math are really things like partial differential equations,
Mm-hmm.
ordinary differential equations, stochastic differential equations. This is
Mm-hmm.
really kind of like my bread and butter.
Mm-hmm.
And arguably for a long time, it wasn't like 100% clear how these things fit into ML.
Mm-hmm.
But then more recently, I would say that like the idea of taking continuous limits of various objects that arise in ML has become immensely fruitful. So when I was a PhD student, I think the kind of trend kind of initiated by Mike Jordan, but many others as well,
Right.
was taking continuous time limits of optimization algorithms, which led to kind of like super clean analysis. There's a line of like famous results,
Mm-hmm.
which kind of showed that you could like understand Nesterov's method and like convergence of accelerated optimization algorithms
Mm-hmm.
from a continuous time perspective, which was much simpler than the traditional discrete time proof. And I thought
Mm-hmm.
that was really beautiful. That's still kind of in like theory land, but that's sort of what was got me kind of like interested in this.
Mm-hmm.
More recently, I think like the amazing observation has been that like diffusion models are
Mm-hmm.
empirically unbelievably successful. They
Mm-hmm.
work very well across a wide range of modalities,
Mm-hmm.
images, video, audio,
Mm-hmm.
proteins, etc.
Mm-hmm.
And this is one of the few examples in ML where somehow like the deeper the mathematical understanding of the models became, the better the models performed. And
Mm-hmm.
this is also unique in that like the language really suddenly became the language of applied math. Like, it wasn't really statistics anymore, but now it's suddenly all about like partial differential equations that describe the evolution of probability measures. You want to push one measure onto another measure. It's about ordinary and stochastic differential equations that describe the evolution of samples as it transforms from one measure into another measure. You need to understand how to integrate these things at inference time to actually generate samples. It's really quite different from the traditional sort of CSML perspective. In particular, like language models are not like this at all, and that's another class of models that's performing amazingly well right now.
Mm-hmm.
So for me, this is kind of the niche, like
Mm-hmm.
sampling, flows, diffusions,
Mm-hmm.
etc. And I think that this is going to be around for a while, not
Mm-hmm.
just because the models work well, but because sampling is a truly fundamental task that
Mm-hmm.
arises all across machine learning, statistics, and applied math and scientific computing.
Mm-hmm.
So I'm like quite optimistic that these models will kind of like bring in a new era in terms of what we can do computationally.
Mm-hmm.
And it's very exciting to me that like at least it appears right now the right way to talk about them and the right way to describe them is the language of applied math.
Awesome. So without further ado, let's go ahead and jump into some of your really exciting papers. We can go ahead and start off with maybe one of your most popular papers titled Stochastic Interpolance, Unifying Framework for Flows and Diffusions. So I guess in this paper at a high level, I mean, there's a lot of different things that you worked on, but I would say like most concretely, you're sort of introducing this powerful unifying framework for generative models and you're sort of bridging these flow-based and diffusion-based methods. Maybe just sort of give us an overview, like what do you think are like the key contributions that you want to mention?
Yeah, so I mean, maybe first I should say that this was collaborative work with
Right.
Michael Albergo and Eric van den Eenden. All of us were at NYU at the time, both brilliant researchers, and I'm really fortunate to have been able to work with them for an extended period of time. So, I mean, this paper really centers around essentially like trying to understand diffusion models in kind of the most minimal and elegant way we possibly can. And
Mm-hmm.
it sort of turns out that like if you really look at what is going on with diffusions, they're
Mm-hmm.
kind of described in terms of this like noising and denoising procedure,
Mm-hmm.
which then itself can be described by a stochastic differential equation. There's a
Mm-hmm.
lot of very nice math. But you can simplify all of this into something called a stochastic interpolant, which
Mm-hmm.
really just it takes samples from one probability distribution, like a
Mm-hmm.
Gaussian. It takes samples from another probability distribution, like images,
Mm-hmm.
randomly pairs them and draws lines between them.
Mm-hmm.
So what diffusion models do is randomly pair these samples, and it
Mm-hmm.
doesn't draw lines, it draws like kind of weirdly curved paths.
Mm-hmm.
And we point out that in fact you can draw any path between them. You can
Mm-hmm.
draw the weirdly curved path that comes up in diffusions.
Mm-hmm.
You can draw straight lines, which ends up being flow matching and rectified flow. You
Mm-hmm.
can draw kind of nonlinear curves that are sort of adapted to the problem domain.
Mm-hmm.
And once you kind of view things in this way, the math simplifies, but then also the learning procedure simplifies. The
Mm-hmm.
algorithms work in a sense better. It's kind of now like the procedure that sort of underlies many of the large scale image generation systems like
Mm-hmm.
Black Forest Labs Flux, Stable Diffusion 3.
Mm-hmm.
And there's also like a really, really nice mathematical theory that emerges where you can kind of characterize the evolution of the Gaussian as it moves towards the target probability measure.
Mm-hmm.
And I think what this framework really exposes is that like diffusion models, in a sense, were much more general than they were originally presented. And in
Mm-hmm.
fact, you don't even necessarily need stochastic differential equations at all to describe them. Like
Mm-hmm.
it's kind of surprising because diffusions were originally discovered using some pretty advanced math. Like you kind of need to know like stochastic analysis. But with stochastic interpolants, you can use stochastic analysis, but you actually don't have to. You can actually use even just kind of like simpler, like basic calculus and kind of like, maybe like freshman or sophomore level ordinary differential equations.
Mm-hmm.
So yeah, it kind of just like exposes really what you can do with diffusions. To what extent can you tailor them to the domain? You can actually use other noise distributions that are not Gaussian. You can change the noising process. You can use kind of exotic processes that are not noising at all.
Mm-hmm.
And for me, this is just like a framework for understanding this class of generative models and also for building them for targeting certain application domains.
Mm-hmm.
So, for example, one thing that I find very exciting is applications of these ideas in the sciences.
Mm-hmm.
And I think that like kind of critical to performance there is going to be actually incorporating domain information about the problem into the design of the generative model.
Mm-hmm.
And that's just something that the stochastic interpolant framework kind of brings like front and center and kind of makes it very easy to do. You often can do these things with diffusions as well, but it's much harder to think about how to do it. So that's kind of, to me, sort of the main contribution, which is kind of like exposing the simple underlying structure and making clear how to actually use that structure to build performant models.
Mm-hmm. Awesome. So I think another paper you had that's honestly also in a very similar sort of topic area is titled like SIT, Exploring Flow and Diffusion-Based Generative Models with Scalable Interpolant Transformers. Maybe just tell us a little bit about how this is different from the first paper, maybe like slightly and like similar in some ways.
Yeah, so this was kind of an applications paper. So the one we just talked about was really a theory paper, kind
Right.
of outlining the framework and explaining like what you can do with it.
Mm-hmm.
And then we wanted to actually show what you can do with it because
Right.
there are experiments in that first paper, but they're small. They're just kind of like
Right.
just demonstrating. So this paper, SIT, I mean, I think really the credit goes to Willis Ma, who's the lead author. He was an undergrad at the time, which is really amazing. And I also want to give a shout out to Saineng Zia, who kind of like led us on the experimental track. He's a computer vision researcher at NYU. He was also amazing in this work. So this was basically the question of like, can you build really large scale models with stochastic interpolants and how well do they perform? So Saineng had previously introduced an architecture called diffusion transformer, or
Mm-hmm.
DIT for short. And the idea was, can we just take that architecture and use it over a stochastic interpolant rather than a diffusion process? We'll
Mm-hmm.
call that SIT, for stochastic interpolant transformer.
Right.
And then can we study how well this model does at large scale? And can we also kind of systematically ablate over the various design decisions that go into training an interpolant model and
Right.
understand, what performance benefits they actually give us?
Mm-hmm.
And what we kind of show is that, like, if you compare a SIT to a DIT, basically an interpolant to a diffusion,
Mm-hmm.
across a range of model scales, I think it
Mm-hmm.
ranges from like 33 million to even much larger than that, hundreds of millions.
Mm-hmm.
At every scale, basically the SIT beats the diffusion model with
Mm-hmm.
the identical training compute. So
Mm-hmm.
like it's really just changing a few lines of code. You're just kind of changing the diffusion process to this simple linear interpolation, and then you just get kind of performance improvements for free.
Mm-hmm.
And on top of that, we show how you can kind of like hack performance and sort of bootstrap and kind of like
Right.
squeeze the most juice out of your model. But the main message is really just that this simple switch leads to improved performance.
Mm-hmm.
Actually, interestingly, Stability AI, which I think is now Black
Yes.
Forest Labs,
Yes.
they kind of at the same time sort of discovered the same thing, and so they have
Mm-hmm.
another paper which sort of does very similar experiments on text to image models and kind
Mm-hmm.
of comes to the same conclusions. So we were pretty excited when we saw that because it was basically like completely independent verification of our results.
Yeah, yeah. Very, very impressive how you guys had a paper that's more on the theoretical side and then chose to follow up with more practical impact. Definitely hope more researchers follow similar patterns. So I guess maybe a last paper we can talk about before we get into the last section of this podcast is you had this paper titled sort of learning stability certificates from data. And this was a paper that I believe you were lead author on, along with Stephen Tu, Nikolai Motny, Jean-Jacques Slotin, and Vikas Sindwani. Maybe just tell us a little bit about this paper.
Yeah, this is a paper now. Like, it's kind of old. This is what I worked on during my original summer internship at
Mm-hmm.
Google, which was Brain at the time, but I think no
Right.
longer Google Brain exists. So Vikas is a leader of a robotics team at Google, and I did an internship on that robotics team with him. This was
Mm-hmm.
during COVID, actually, so everything was remote.
Mm-hmm.
So Stephen is a good friend of mine. We've now met in person many times, but
Yeah.
we became friends through working on this paper and other
Nice.
papers together, and it was entirely virtual for like 2 years.
Of course.
Yeah, so the basic idea is simple. So like at the time, and this is still true, people were training these like big reinforcement learning policies for robot control.
Mm-hmm.
But now you want to deploy these robots in the world, and you actually want them to be safe. You want to make sure that the robot doesn't like do something crazy, become
Mm-hmm.
unstable, hit someone, break something.
Mm-hmm.
Like especially if you want to actually like have humans in the home or like
Mm-hmm.
driving cars and things like that. Sorry, robots in the home or like driving cars, things like that. So the question is like, how do you like ascertain safety?
Mm-hmm.
And it turns out that there are rigorous tools from control theory called
Mm-hmm.
Lyapunov functions
Mm-hmm.
that tell you whether or not a system is stable. In other
Mm-hmm.
words, like, is there some trajectory that kind of attracts all other trajectories? So if you perturb the system, it will sort of just come back. And this is kind of what you want to determine stability, because then, say, if your robot is walking, it means, if you knock it a little bit, well, it will just kind of like fall back onto the walking trajectory. It won't be that like you knock it and then this grows crazy unstable and it does something wild from that
Mm-hmm.
point onwards.
Mm-hmm.
So we wanted to understand if we can come up with Lyapunov functions for these learned reinforcement learning policies.
Mm-hmm.
The issue is that the way you typically come up with them in control theory is you just kind of write them down. They just sort of come out of magical intuition that the designer has for the system.
Mm-hmm.
So the idea was to learn it. So you first train an RL policy, you then
Mm-hmm.
run a bunch of trajectories on the system, you gather a bunch of data, and then you try to learn a stability certificate in the form of a Lyapunov function from those trajectories.
Mm-hmm.
And what we do is we essentially introduce a number of learning objectives that actually enable you to learn these Lyapunov functions, and we show
Mm-hmm.
that you really can do it in practice, both in
Mm-hmm.
kind of synthetic examples and on simulated robots. At the
Mm-hmm.
time, we had to do simulations because everything was closed down due to COVID.
Mm-hmm. Yeah, awesome. So I guess maybe tell us a little bit about some of your advice that you would have for researchers. I mean, obviously, you sort of spent some time both in grad school at Harvard, but even, honestly, an undergrad at Northwestern, triple majoring and sort of getting access to all of this. Maybe we can sort of split it into a few sections. Maybe advice for undergrads that are interested in getting PhDs, advice for PhD students that are working on research, and then maybe just generally advice for researchers on, how to pursue meaningful research directions.
Yeah, I mean, it's a great question, and it's a really hard question. I think it's a
Yeah.
question that like junior faculty, probably even senior faculty, are sort of grappling with all the
Right.
time. Like, how do I pick what exactly I should work on?
Right.
So this is something that should be taken as like I'm still finding my own answer to this question.
Right.
I am on my own journey here, but um, I mean, I think at a high level, I've always just been kind of attracted to this idea that like the reason we do academics, the reason we go to school, the reason we do a PhD, the reason we want to become a professor
Mm.
is because we think the work is beautiful and we think it's interesting and
Mm.
we want to pursue it for its own sake,
Mm.
right? I think fundamentally, if you're doing research, you should be researching things that you are interested in,
Mm.
not things that you think the community will, is going to be hot right now or whatever
Yeah.
is kind of like the next topic that might
Right.
get you a fancy job in industry. So this has sort of always been my approach, which is like, what are topics that I really want to learn about, that I
Mm.
really want to personally understand, and how can I find research projects that will teach me about those things? So
Mm.
I always wanted to understand dynamical systems. That's why I got into control theory. That's why I got into generative models. Right now I want to understand more what's going on with language and what's going on with fine tuning and things like that. So I'm learning tools related to discrete diffusion and stochastic optimal control. Always just trying to like identify some objective and then design a research path that will actually lead me to achieving that objective.
Mm.
So that would really be my main recommendation, which is that when picking, like deciding whether or not to do a PhD, for
Mm.
example, the question should be like, do you really want to do that work rather
Mm.
than do you just want to have a PhD, or do you think it's going to get you a good job? You can get
Mm.
a good job other ways.
Mm.
Just having a PhD, that goal will become less interesting when you're 3 years into the
Mm.
stressful grind of PhD. So you should always just be pursuing something that you personally find fascinating, and if you find it fascinating, then others won't be able to compete, because you'll
Mm.
be doing it for fun. You'll be doing it
Indeed.
because you really enjoy it. And I think that is really the way to success in my mind.
Mm. Awesome. Well, without further ado, huge thanks to Nick. Thanks for coming on the podcast. Really appreciate your time.
Thanks for having me.